General relativity, step by step. I've written out the Schwarzschild metric here, and I just want to introduce a few simplifications that will make our life easier. The first one is to notice that these terms here, these two terms here, the theta term and the phi term, are the same in ordinary flat Minkowski space as they are in Schwarzschild space. And so, quite often, you'll rewrite that as r squared d uppercase omega squared, where d omega squared is just d theta squared, that term there, plus sine squared theta d phi squared. It's just the same in flat space as it is ordinary space. And we'll make use of this fact later on. But notationally, we use this d omega squared term here. So what we've got left now is ds squared equals minus dt squared 1 minus 2 gm over r plus dr squared over the same thing, 2gm over r, plus r squared d uppercase omega squared. And this makes it easier to separate out the radial from the non-radial components of motion. Quite often, you choose units in which big G equals 1. Now G equals 6.671 times 10 to the minus 11 in SI units. And you can make G equals 1, and you do this by choosing your unit of mass suitably. So it's just a straightforward calculation as to what that unit of mass is. So we've got ds squared equals minus dt squared in just the same way that we choose the speed of light equal to be 1 as well. By choosing we can always make the speed of light equal to 1 by choosing our unit of length and our unit of distance appropriately. I'll come back to that in a minute. But for the moment, we're just going to focus on choosing the unit of mass appropriately. And now we've got minus dt squared 1 minus 2m over r, where m is the mass of the black hole, plus dr squared over 1 minus 2m over r, plus r squared d omega squared. I just want to come back to the fact that the speed of light equals 1. Speed of light. C equals 1 by choosing the units of time and of distance appropriately. So if we choose our unit of time to be 1 second, time unit equals 1 second, then our distance unit equals distance travelled by light in 1 second equals 3 times approximately times 10 to the 8 meters. Alternatively, we can choose our distance unit to be equal to 1 meter, and in which case our time unit will be 1 meter divided by 3 times 10 to the 8 meters per second equals 3 times 10 to the minus 9 seconds. Yeah, that's right. So if our distance unit is 1 meter, then our time unit is some tiny, by our standards, tiny unit of time. And of course, if our unit of time is 1 second, then the distance that light can travel in that time is enormous. It's 3 times 10 to the 8 meters, huge distance. By our standards, by our terrestrial standards. So I can choose the time unit to be anything. I can say the time equals 14 days if I want, and that will give me a unit of distance. I can choose these things to be what I like, and the speed of light is still equal to 1. So let me just write out the Schwarzschild metric. It's minus dt squared 1 minus 2 gm over r. Actually, I'm going to put the units back in. Plus dr squared. I think I've been writing x sometimes. Oh no, there's an r here. Sometimes I think I might slip up and write an x by mistake. 1 minus 2 gm over c squared r plus r squared d omega squared. Well, what I'm going to do is I'm going to choose 2gm over c squared to be equal to 1. And I can do this simply by choosing, mass, length, and time units so that c equals 1, and so I've got also 2gm over c squared equals 1. Okay? So let's figure out what that actually is in the case of a real object. G equals 6.671 times 10 to the minus 11 in SI units. M equals the mass of the black hole. And I'm going to say it's 10 solar masses. That's the symbol for solar mass. Equals 10 times 2 times 10 to the 30, I think it is, kilograms. So we've got 2 times 10 to the 31. And of course c equals the speed of light, which is 3 times 10 to the 8, approximately. So what does that give us for a unit? See, I'm just choosing a sensible sized black hole, and a 10 stellar mass black hole is, I guess it's a reasonably small one. There are bigger ones out there, much bigger ones out there, but we'll start with this one. This is a standard assumption. Okay, so I'll fire up my R window here, which is here. I'll just move that into scope here, just make it a bit larger so we can see what we're doing. Try that again. There we go. If I go edit, GUI preferences, take the text up to something that's actually visible, not microscopic. Okay, so what we've got, what we want is 2gm over c squared, and of course it won't work because it doesn't know what that is. 2 times 6.671 times 10 to the minus 11 for the G, times the mass of the black hole, 10 stellar masses, and the mass of the sun is 2 times 10 to the 30 kilograms, divided by 3 times 10 to the 8 squared. And we have got a result of 29,000. We've got a result of about 30 kilometers. And of course, if I want the unit of time, all I do is have to divide by c cubed instead, which gives me about 10 to the minus 4 of a second. So let me just write those down. We've got 30 kilometers and about 10 to the minus 4 of a second. If I go back, where is it? Oh, it's this one. So unit of time, unit of distance equals approximately, was it 30 or 15? There's a factor of 2 which always drives me nuts. It was 30 kilometers. 30 kilometers for a 10 stellar mass black hole. And our unit of time was approximately 10 to the minus 4 of a second. 10 to the minus 4 of a second. And with these units here, 2gm over c squared equals 1. So I can rewrite my Schwarzschild metric in a much more easy much more easy way, because this group here, 2gm over c squared equals 1. And so what that means is that ds squared equals minus dt squared, 1 minus 1 over r, plus dr squared over 1 minus 1 over r, plus r squared d omega squared. But of course, for reasons I don't understand, nobody seems to use these units, but I'm going to use them, and I'll show you in the next screencast. dt squared 1 minus 2gm over r. Again, well, you see, this is the way you'll see it in most of the literature. Actually, with big G not there, you'll see it in most of the literature like that. But if you're going to set g and c equal to 1, why not just set the unit that you're interested in, which is 2gm over c squared? It defeats me. Plus dr squared over 1 minus the same thing, 2m over r. This is now in geometrized units. Plus r squared d omega squared. Okay, well, I've spent long enough talking about that. I will alternate between this form and this form, depending on... Well, actually, I'm going to use this form nearly all the time. But you've got to bear it... But I'll just remind you that we've got this unstated dependence here. Okay, that's the Schwarzschild metric. And I'm going to stop there. Stop.